So let's go ahead and get started. Upon completing this particular module, hopefully you will be able to meet the following objectives: identify components of various digital imaging systems, compare different digital systems, discuss image receptors, especially those that are used in digital imaging, as we are very familiar with those that were used in film screen. We will discuss the image acquisition process for both computed radiography and digital radiography. We will talk about the construction and the characteristics of the photostimulable plate, and we'll explain the differences in direct and indirect capture DR systems. We also hope to explain the role of charge-coupled devices in digital imaging systems, and we would like to discuss the factors that affect spatial resolution in digital imaging, some of which are very similar to what we learned in regular radiography. We will talk about the process of image extraction and the process for CR and DR systems. And finally, we will describe factors that affect digital image quality. So we have a lot right now that we plan on covering. So hopefully you will renew your learning in DR and CR and maybe at least learn something a little different or new. So again, in this module, we will try to cover the development of digital imaging, and those subtopics will be film screen imaging versus digital, historical development, the types of digital radiography systems, the comparison of film and digital imaging, and the rationale for why we moved to digital imaging. And finally, we'll talk a little bit about the advantages of digital imaging. So, radiographic imaging has undergone vast changes in the last 40 years. Digital imaging is one of the most important of those changes. Digital imaging has been possible since the introduction of computed tomography. Computed tomography, which became available for clinical use, as many of you may remember, in the 1970s. And it was the first imaging modality to combine medical imaging technology with computer technology. MRI, ultrasound, and nuclear medicine continued this trend over the next decade. In the past 20 years, though, diagnostic radiography has joined the move to digital imaging. The Fuji Corporation introduced the first version of digital imaging when their computed radiography, or CR system, entered the market in 1983. A number of other manufacturers now have CR equipment on the market, and you may be familiar with many of them. When it was first introduced, CR had a number of problems that were associated with high cost, poor image quality, and of course, limitations in the computer technology that was available at the time. As computer technology improved, and as more vendors entered the marketplace, the aforementioned problems were resolved. Digital imaging has now become the gold standard for medical imaging departments and is employed in every imaging modality. So, digital imaging can be divided into two major categories: computed radiography and digital radiography. These systems can be differentiated by the type of image receptor that's used. CR systems use a photostimulable storage phosphor plate known as a PSP, or sometimes known as an IP, as the image receptor for this system. The IP is housed in a cassette that is very similar to a film screen cassette, for those of you who remember that. Once it's exposed to X-rays, the IP must be processed in a plate reader to transform the latent image that's stored there in the IP. The IP must be erased prior to being used for subsequent exposures. Digital, or DR, on the other hand, usually refers to an image receptor that may be inside of a device that bears some resemblance to a traditional cassette, or the image receptor may be part of the X-ray equipment itself and never handled by the radiographer. In either case, once the exposure is taken, the image data is sent to the computer, and the image receptor is immediately ready for the next exposure. So that's one of the main differences between computed radiography and digital radiography. Again, in computed radiography, the plate must be erased to be used again. In digital radiography, it is immediately ready for the next exposure. DR uses flat panel detectors with thin film transistor technology that are categorized as direct capture or indirect capture. So let's look at the basic differences and compare film with digital. The basic differences between conventional film screen imaging, computed radiography, or CR, and direct digital radiography, or DR, are the image receptors that are used to capture the latent image, and the methods that are used to transform that latent image into a manifest or visible image. Those terms, latent image and manifest image, were terms that we all learned when we went through our radiography programs. Again, DR often refers to cassetteless systems, whereas CR uses a cassette with an imaging plate. So why did we move to digital? Digital images are composed of numerical data that can be easily manipulated by a computer. Image brightness, or visible density and contrast, can be altered by the computer during what we know as post-processing. Therefore, regardless of the original exposure factors, within reason, of course, any anatomical structure can be optimally visualized. So it has become faster, cheaper, safer, and better. And it was driven by the demand for high performance, lower radiation dose, if used correctly, better staff productivity, and a pressure to reduce healthcare costs and increase efficiency, which I am sure many of you have seen in your institutions. Again, some advantages of digital imaging. Several advantages over film screen imaging. For example, it provides increased contrast resolution, which really means more shades of gray are available based on the pixel bit depth of the system. It also can promote greater productivity from the workforce because digital imaging potentially allows for fewer steps in the image processing. Departments can increase throughput or serve a greater number of patients during the day. And unlike film screen imaging, digital images allow for manipulation and enhancement in post-processing. Another real advantage is that images may be electronically transmitted for consultation with providers in other locations, including distant countries. Images can be viewed by many caregivers simultaneously, and they're not lost in that process. And finally, digital images have a wider dynamic range because they exhibit a linear response to X-ray exposure. A relatively large number of exposure values can be used to produce a diagnostic image. These advantages will be explained in greater detail throughout the series. Film screen systems are considered analog imaging due to the continuous series of grays that the signal records on the image receptor, or film in this instance. In digital systems, CR and DR both, the image signal is a series of individual discrete values, not shades of gray. Digital image receptors respond to a wider range of X-ray exposures, resulting in a wider dynamic range. The response of each system can be illustrated by comparing the D log E, or the H and D curve of a digital image receptor and the film screen image receptor. As you can see in this illustration, the digital IR response is linear right here and extends straight up. And therefore, a greater number of density values can be displayed, as opposed to the film screen response, which reaches a point where shades of gray cannot be distinguished. That's known as the D max. So here you can see this is not linear. It comes up and it reaches a point where there are no more shades of gray that can be seen. Whereas with digital, it continuously goes up. So DR or CR, is there really a distinction? Well, not really. CR is digital imaging, but it's the earliest form of digital radiography. So in this particular series, we will refer both computed radiography and digital radiography, CR and DR, as digital imaging. Both are digital imaging processes, and the only distinction really is being the image receptor that's used in CR, which was, as we said, the earliest form of digital imaging. So let's look at the computer radiography, or CR, and we'll look at some of the subtopics, such as the imaging plate, the latent image formation, the plate reader itself, and of course, the PSP, or photostimulable phosphor plate cycle. So we can see how that all transforms through the reader. So the imaging plate. The PSP, or IP, is held in a cassette that's made of a lightweight plastic or sometimes carbon fiber. The front and the back are lined with felt-like material to prevent static buildup and dust collection. CR cassettes look like film screen cassettes, but unlike film screen cassettes, the CR cassette does not have to be light tight because the IP is not sensitive to white light. The back panel is a sheet of lead foil, or sometimes aluminum, that's used to absorb X-rays that penetrate the plate. The purpose of the lead foil is to reduce the amount of backscatter radiation that strikes the plate. This is very similar to a film screen cassette. Each CR cassette has a memory chip that's installed in that back panel, and that memory chip records the patient's demographics. So here we see a picture of a photostimulable phosphor plate and the layers. A plate is approximately 1 millimeter in thickness, and it's made of several layers, which are very similar to an intensifying screen that's used in film screen radiography. The protective layer is made up of a thin, clear layer of plastic that's used to protect the phosphor and to improve the signal to noise ratio. We see that here on the top. The phosphor, or active layer, contains what we know as the storage phosphor, right here in green. The conductor layer reduces and conducts static electricity away from the plate, and it absorbs light to increase the spatial resolution. That's the middle here. The color layer may be present in newer plates, and it is used to absorb stimulating light and to reflect emitted light. The light shield, or reflective layer, reflects light that's being released during the reading phase of the plate. And the supportive layer, seen here, is made of a sturdy material that gives rigidity to the plate. And the backing layer is a soft layer right here that protects the back of the plate. Sometimes these layers may have different or alternative names depending on the source of information that you see them in. So the imaging plate. The imaging plate is coated with emulsion on one side. Therefore, the plate has to be loaded in the holder or cassette facing up. Phosphors that are used in CR imaging plates are referred to as photostimulable storage phosphors. The phosphors must have the ability to absorb energy, store energy, and release the energy upon proper stimulation or excitation. Certain barium fluorohalide compounds exhibit these types of characteristics. Europium is a silvery rare earth metal that is used as an activator for the phosphor. Europium captures some of the energy of the remnant X-ray beam. It is responsible for the phosphor's ability to store energy. Here we see a formula that indicates that certain halides can be interchangeable, such as bromide, iodide, gadolinium, and strontium. And we see the chemical formulas for bromide and iodide. The atomic number for europium is 63. So we're still talking about the imaging plate, but let's talk about turbid phosphor. Phosphors that are used in digital imaging can come in two forms. The phosphors that are pictured here are referred to as turbid phosphor crystals. These are randomly distributed, as you can see, with the active layer of the PSP. Typically, phosphors of this type are barium fluorobromide, barium strontium fluoride bromide, gadolinium oxysulfide, and rubidium fluoride. They are termed turbid due to their crystal structure, and of course, this structure does have some drawbacks. There is a decrease in spatial resolution with turbid phosphors because light emission is in all directions, causing more spreading of all the lines making up the image, which increases penumbra. As you are well aware, penumbra is the unsharpness that's in an image. The second type of a phosphor structure that can be used in digital imaging is called needle structure or columnar phosphors. These are grown in controlled settings to form a needle or a column arrangement. As can be seen in this particular slide, these phosphors resemble needles that are standing on edge. This structure, though, results in less light diversion and therefore better spatial resolution. Cesium iodide is an example of this type of phosphor. So, latent image formation and image acquisition. During exposure of the imaging plate, electrons within the phosphor crystals are moved from their normal energy level to a different energy level within the crystal. This entire area here is the crystal. The steps of this process are as follows. the X-ray photons that exit the patient following exposure hit the phosphor crystals, and they cause electrons to move from their normal orbital location to a higher energy level. Approximately 50% of these electrons become trapped in the conduction band of the phosphor atom. Here is the conduction band, and here is the trap. Some of these higher energy electrons spontaneously return to their resting energy state by emitting energy in the form of light. Europium is the phosphor that's responsible for capturing the electrons and causing them to be stored in the F centers traps. And these electrons that are not captured migrate back to the valence band. So following X-ray exposure, the remnant beam exits the patient and interacts with the electrons in the phosphor of the imaging plate. This results in an energy transfer. This transfer of energy causes excitation of the electrons into a metastable state. Some of the electrons return to their ground state and emit a blue-violet light. The phosphor crystals develop defects called metastable sites, or F centers, or color centers. These F centers are small electronic holes that trap or capture the electrons that are released from the phosphor atom. The latent image is formed by these electron holes, or F centers. As we previously stated, the trapped electrons will comprise the latent image. The imaging plate must then be inserted into the plate reader to release the electrons and to process the latent image. A helium neon laser light scans the plate and releases the electrons that are trapped. These electrons emit light, and as they move back and forth to the valence band. And the imaging plate is scanned by finely focused neon helium laser beam in a raster pattern. A raster pattern is also known as an image or bitmap, and it is when a plate is scanned from left to right and top to bottom. So here's an image of a plate reader showing where the cassette is placed as it opens up and the imaging plate comes out and follows along the system. The design of the plate reader varies by vendor, but they all have the same components. The drive mechanism along here moves the plate through the scanning process. The optical system is made up of a laser, beam shaping optics, light collecting optics, and optical filters. The optical system is designed to protect and guide the precisely controlled laser beam back and forth across the plate, as we talked about as a raster pattern. The photodetector is used to sense the light that's released from the plate during the scanning. And the ADC receives light and converts it into electric signal. As the plate comes back up, it will be erased through the erasure area before it is put back into the cassette. The cassette containing the image plate is inserted into the plate reader, as we said, and the image plate is removed by the drive mechanism. The drive mechanism slowly moves the plate through the reader. The helium neon laser, or solid state diodes in some newer plate readers, is directed to the imaging plate while the plate is moving throughout the system. The laser scans the plate in a raster pattern, again from left to right, stimulating the trapped electrons and freeing them from the F centers. As the plate moves, an oscillating mirror deflects the laser beam, and it goes back and forth across the imaging plate. The laser scan then allows the electrons to return to a lower energy state, referred to as photostimulated luminescence, which is the emission of blue-violet light. The intensity of the light emission is in proportion to the amount of radiation that was absorbed by the imaging plate in any particular area of the imaging plate. The visible light that's given off by the IP at this stage is emitted in all directions. It must be channeled by the fiber optic collection that we saw in the previous slide, that assembly which will direct the emitted light to one or more photodetectors, photomultiplier tubes, otherwise known as PMT, or to a charge coupled device, also known as a CCD. The photodetectors convert the visible light into an electronic analog signal. The analog signal is sent to the analog to digital converter, otherwise known as the ADC, for conversion into a digital signal, which is numerical, that can be read and used by the computer and used to create the manifest image. So once the plate has been scanned and the image data has been sent to the analog to digital converter, the plate is erased by exposing it to intense white light. This forces the holes or traps to release any residual electrons that may be in there. Following erasure, the IP is ready for use again. Overexposed plates may need to be erased more than once because they will retain some of the previous energy. CR imaging plates are more sensitive to background scatter and should be protected prior to use. and erased if they have been stored for any length of time. Once used for a patient exam, the plate should be scanned immediately or as soon as possible, because it will begin to lose some of the energy that's stored, which is actually the image data. It is estimated that the plate will then lose approximately 25% of the latent image in about 8 hours. So, analog to digital conversion. Quantification or digitization refers to the process of converting the analog, which is electric, signal to image into numerical data. During this process, a numerical value is assigned to each light photon. In this process, each phosphor storage center is scanned and the released electrons enter the ADC that divides the analog signal into a matrix. And each pixel in the matrix is assigned a digital or numerical or brightness value that represents the amount of light that was emitted from the surface of the imaging plate during scanning. Pixels that have received more exposure are assigned values that represent less brightness, and they will appear darker on the displayed image. Pixels that receive less exposure are assigned values that represent more brightness, and they will appear lighter on the displayed image. All brightness values together make up the raw or image data.